Hi everyone, this is Dr. Mahender, Associate Professor of Mathematics, Department of Basic Science and Humanities, B.V. Raj Institute of Technology, Narsapur. The course name is Linear Algebra and Calculus. The topic name is we are doing the problems on diagonalization of a matrix. So, before going to today's class, just I recall the previous session. So, in the previous class, we started the diagonalization of a matrix. So, we started with the first problem, the non-symmetric matrix. So, generally if the matrix is non-symmetric, generally may or may not diagonalizable. That is depends on the finally the number of linearly independent eigenvectors. If number of linearly independent eigenvectors equal to the order of the matrix is diagonalizable. If less than order of the matrix, number of independent eigenvectors is not diagonalizable. Okay. So, first problem we already this work out already this problem. This first one is the matrix A is 1 0 minus 1 1 2 1 2 2 3. Now, this problem we have done in the previous class, and for this we got eigenvalues, we got 1 2 3 because the matrix is non-symmetric. Now, look at the matrix nature is the non-symmetric matrix. If the matrix is non-symmetric, generally may or may not diagonalizable. Compulsory we have to find the eigenvalues. If eigenvalues are distinct, the compulsory the number of eigenvectors will equal to the order of the matrix. What is the order of the matrix here? 3 by 3. Order is 3. Therefore, if the eigenvalues are distinct, definitely it is diagonalizable. It is diagonalizable. Already we diagonalized this matrix, but today I am going to concentrate on two more matrices. The next matrix is what? 3 2 2 1 2 2. Second row is the 1 2 2. This is a minus 1 0. It is also 3 by 3 matrix. The third problem is 3 2 2 1 2 1, the minus 2 minus, it is also 3 by 3 matrix. Now, look at all are the non-symmetric matrix. This is also non-symmetric matrix. It is also non-symmetric matrix. Now, look at because of A transpose not equal to, it is also non-symmetric matrix. Generally, non-symmetric matrix may or may not diagonalizable. May or may not diagonal. Compulsory first we have to find the eigenvalue. If eigenvalues are distinct, automatically it will be diagonalizable, but eigenvalues are repeated case, may or may not diagonalizable. So, this case come to this case, this is what minus 1 will get eigenvalues are this one 1 2 2 will get. What is the nature you will the eigenvalues here? The nature of the eigenvalues is the not distinct, but in such case the total number of eigenvectors will get only 2 only you will get. For 1 you will get only 1, well this 1, but this 2 repeated roots will get only one eigenvectors. Finally, number of eigenvectors, how many eigenvectors? 2, which is less than order of the matrix. What is the order of the matrix? Order of a matrix. What is the 3? Therefore, this is a not diagonalizable. Why? Because the finally you look at the number of eigenvectors only. If the number of eigenvectors equal to the order of the matrix, this matrix is diagonalizable. Okay, but coming to this third matrix, lambda is equal to, we will get for this one 1 1 2. Here also eigenvalues are not distinct, but for this matrix we will get eigenvectors 1 2. For the repeated roots 1 1 will get the 2 eigenvectors, and x3 is for this 2. So, totally how many eigenvectors we have? So, number of eigenvectors equal to 3, that is equal to order of a matrix, order of the matrix. order of the matrix. Therefore, this case diagonalizable. Now, just by these three example, what we have to conclude that if non-symmetric matrix, particular these are the related to non-symmetric matrix. If eigenvalues are distinct, we can say directly diagonalizable. Just you can do the process. But if eigenvalues are repeated, may or may not diagonalizable. May or may not diagonal. So, this is the example for second and third. Now, look at the second one. Eigenvalues are repeated. So, but it is not diagonalizable. Why? Because finally the number of eigenvectors is less than order of the matrix. But third case, look at the third case here. The number of eigenvectors, this is also repeated eigenvalues, number of eigenvector but equal to the order of the matrix. Therefore, this case is diagonalizable. So, we will do the second one now. Is the matrix this is what 3 2 2 1 2 2 -1 -1 0 diagonalizable. This is the question. Now, look at what is the matrix. Is it symmetric or matrix? Now, what is the A? A is 3 2 2. The second row is the 1 2 2. Third row is the -1 0. It is a 3 by 3 matrix. Is it symmetric or non-symmetric? How to check it symmetric, non-symmetric? Just look at the first row and first column. What is the first row? 3 2 2. What is the first column? 3 1 -1. If the first row is not identical with first column, symmetric means the all rows, the corresponding rows and corresponding columns are identical. The first row is identical with the first column, second row is identical with the second column. Like similarly, third row is identical with the third column. We can say that symmetric. So, we can write A transform is equal to A. But if fail anyone that first row is not identical with first column means it is non-symmetric matrix. Therefore, A transpose A is a non-symmetric matrix. Non-symmetric. But non-symmetric we cannot say by directly saying. If symmetric we can directly say it is a diagonalizable. Compulsory what we would do? Find eigenvalues. For that we need to compute Katsik equation. What is the Katsik equation of the matrix? Katsik equation determinant of A minus lambda equal to 0. This is the main principle. But here using the shortcut formula, lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0. So, better you have to use this formula directly. We will get the for 3 by 3 matrices. What is the equation you have to remember? The shortcut formula lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0. Here what represent S1? S1 is the trace of the matrix, the sum of the principal diagonal element. S2 is the what? The sum of the minors of the principal diagonal element. S3 is the determinant. We will do that one. Okay, where S1 is equal to trace of the matrix. What the trace? The sum of principal diagonal element. 3 plus 2 plus 0 is equal to 5. S2 is sum of minors of principal diagonal element, minor of A11, minor of A22, minor of A33. So, minor of A11 is obtained by deleting the first row and first column. What we will get? 2, 2, minus 1, 0. Minor of A22 obtained by deleting second row, second column. That is 3, 2, minus 1, 0. The same way, the minor of A33 is obtained by deleting the third row, third column. This is 3, 2, 1, 2. Okay. This is the 2. This is the 2. This is the 5 minus 5, 6 minus 2, 4. So, the answer is 8. Answer is 8. Now S3 you can calculate determinant of the matrix. What is the determinant? The sum of products of elements of any row or any column with corresponding cofactor with respect to first row will do. So, plus minus plus 3, this is 0 plus 2 is a 2, will get minus 2, 0 plus 2. So, deleting this first column and first row and second column, this elements you write it 0 minus minus plus 2, then come to this one 2, yeah. This is the minus 1 plus 2, minus 1 plus 2 is the 1 will get, simplifying this one 6 minus 4 plus 2. So, we will get the 4 will get. Therefore, the equation is what? Lambda cube minus 5 lambda square 8 lambda minus 4 is equal to 0. S1 is equal to what we got? S1 is equal to 5, S2 is equal to 8 and S3 is equal to 4. Now, we got the equation, quadratic equation. Then what we do now? Find the roots of this equation because of third degree. So, by inspection you can find one root, start with 1, put lambda is equal to 1, put lambda is equal to 1, the minus 1, minus 5 plus 8 minus 4, the 9 0. So, by inspection this lambda is equal to 1 is a root, Then what we do next? If lambda is equal to 1 is a root, then use the synthetic division formula, write the coefficient decreasing order, 1 is the minus 1, 5, 8. Hope we know everything, everyone this concept. So, you start with 0, add here 1, multiply and write it here 1. This is the minus 4, 4, 4, 4, yeah, 0. If we get last 0 means the process is correct. Okay. Now, lambda is equal to 1 is the root, means lambda minus 1 is a factor. Then these are the coefficients of second degree, lambda square minus 4 lambda plus 4 is equal to 0. Now, this is the lambda minus 1, this you can write it as lambda minus 2 whole square. So, lambda is equal to 1, 2, 2. What is the nature of eigenvalues? Eigenvalues are not distinct. If distinct, here itself we can conclude, but if not distinct we cannot conclude by just observing the eigenvalues. Compulsory we need to find the eigenvectors. So, finally look into the number of eigenvectors. If the number of eigenvectors equal to the order of matrix or less than order of matrix, if number of eigenvectors equal to the order of matrix, in that case the matrix is diagonalizable. Suppose number of eigenvectors less than order of matrix, in that case the matrix is not diagonalizable. And one more also you have to remember, after getting the eigenvalues you check it whether these are correct or not. Then how to check it? That one, the sum. What is the sum? What is the sum? The sum is 1 plus 2 plus 2, 5. This is equal to the what? The trace of a matrix. So, the first condition is satisfied. Then the product. What is the product? 1 dot 2 dot 2 is equal to 4. That is equal to determinant of the matrix. So, satisfied. So, therefore, these are the correct. So, before proceeding to the eigenvectors, compulsory check it by these two properties. Okay. So, we will move to the eigenvectors. The first, for lambda is equal to 1, we will do a minus lambda 1, I means 1 I of x is equal to 0. What is the I? The corresponding identity matrix you have to take it, the I3 you have to take it, already A. but the impact is only on the diagonal when we subtract in the identity matrix. Just you can subtract 1 from diagonals. So, will become what? A minus I, 2, 2, 2, 1, 2 minus 1 is the 1, minus 1, minus 1, 0 minus 1 is the minus 1. This is what x1, x2, x3. Okay. So, therefore, better here common is there, that multiplicity, just I am dividing that one, 1, 1, 1, I am dividing by 2 R1. Okay. This is 1, 1, 1. This also you can multiply with R3, you will get 1, 1, 1. Now, what we have to do? We have to find the rank, solve the system. For that, we can find the rank by echelon form. I am using the echelon form concept. Okay. So, that R1, this is the key element, using this as a key element. Now, this one you make it 0 and this one make it 0. What are the operations? Tell me, guess easily. The R2 minus R1, R3 minus R1, and this means we are changing R2 as R2 minus R1. So, rho 2 minus rho 1 as a rho 2, I am modifying, rho 3 minus rho 1 as a modifying as a rho 3. So, R1 is the same now. This one what? 1, 1, 1, 0, 0, 1. This is 0, 0. Now, look at, we are reduced the, we cannot reduce furthermore, we reach the echelon form. Once you echelon form, what is the rank? Number of non-zero rows is the rank is 2. You compare with number of unknowns is 3. So, therefore, this is the R, this is the n. What is the n minus R? Is the 3 minus 2 is the 1. We know the what is the significance of this one, hope everyone knows. So, this will tell us how many unknowns assigned arbitrarily. By assigning one unknown arbitrarily, we are going to solve this system. So, finally, what are the equation will become from this? x1 plus x2 plus x3 is equal to 0. Here x3 already 0. N1 you will take it as a x1. Let x1 is equal to k, then x2 will become what? Minus k. Therefore, x is equal to x1 k minus k 0, means 1 minus 1 0 k, that is equal to x1 k. So, where x1 is eigenvector for lambda is equal to 1. Then next third, for lambda is equal to 2, you will write it. 1 is the one, a minus 2y of x is equal to 0. What is the a minus 2y? Subtract 2 from the diagonal, so we will get 1, 2, 2, this one non-diagonals will write the same. So, only the subtract 2 from diagonal, remaining are same. 1, 2 minus 2 is the 0, minus 1, minus 1, this is what is the minus 2. Yeah, here we will write x 0. Okay. But what are the operations you will write? R 2 minus R1, R3 plus R1. So, we will get 1, 2, 2, 0, minus 2, 0, add this R3 plus R1, 0, 1, 0. So, finally, what you do it? This is will become 0 multiplied. This is 1, 2, 2. This is also minus 1. I am taking minus 1, 0. This also will become 0 after that. So, rank is what? 2. Rank is 2 less than 3. N minus R is equal to 1. What will get the system? x plus x1 plus 2x2 2x3 is equal to 0 and x2 0. So anyone you will take, it means suppose if you take x3 is equal to k because of n minus r1. So therefore what you will get, x is equal to minus k, x3 is equal to x1 is equal to minus 2k you will get, and the minus 2k, the minus 2 will get this x2 0, x3 is equal to k. So therefore what is the x2? K, where x2 is what? Eigenvector for lambda is equal to 2. Now look at finally how many eigenvectors we got it? Only 2 eigenvectors. One x1, one is x2. But what is the order of the matrix here? Order of matrix is what? 3. So therefore the number of eigenvectors is not equal to the order of matrix. So therefore what you have to conclude? Therefore just I am writing here, since A having only 2 linearly independent eigenvectors which is less than its order. What is the order? 3. Therefore A is not diagonalizable. So why? Because the finally, for look at here, for lambda is equal to 1, we got only one eigenvector, that is what? 1 minus 1 minus 2. But look at this one, for repeated roots, for 2 we got only one eigenvector, that is x2. So finally total how many eigenvectors we got it? Only we got 2 eigenvectors. So the number of total number of linearly independent eigenvectors are how many? We got only 2, since A having only 2 linearly independent eigenvectors which is less than its order. Therefore A is not diagonalizable. Suppose for this particular 2, if you exist 2 linearly independent eigenvectors, it is diagonalizable. But coming to this one, yeah, this because of what we have done, third one, this second one we did is here, we got 1 2 2. For 1 we got eigenvectors 1, but repeated root this 2 we got only one eigenvector. Finally totally we got only 2 eigenvectors, but is less than order of the matrix, therefore it is not diagonalizable. But coming to this problem, just you have to work out as a homework this one. For this one, eigenvalues are not distinct, we will get repeated eigenvalues, but 2 will get one eigenvalue, let us say 1. But repeated roots here, the repeated roots will get the 2 eigenvalues. So totally how many eigenvalues we got it here? 3. Therefore here the matrix is diagonalizable. But even though eigenvalues are not distinct, but this matrix is diagonalizable. Why? Because the number of linearly independent vectors finally we got it equal to the order of the matrix. So from these 3 examples from non-symmetric matrix, when it is diagonalizable, when it is not diagonalizable, irrespective of the eigenvalues are repeated. I covered one example, diagonalizable, that is the third one. If eigenvalues are not repeated, not repeated is the one of the example is what? Repeated. For not eigenvalues, sorry, the eigenvalues are repeated, it is diagonalizable. Sorry, just I want to once again quickly recap this one. If eigenvalues are distinct, it is a diagonalizable, but eigenvalues are repeated, may or may not diagonalizable. Eigenvalues are repeated means eigenvalues are not distinct. So one problem covered not diagonalizable, one problem covered for diagonalizable, which case eigenvalues are not distinct, that is what? Repeated case. So repeated case may or may not diagonalizable. So one problem covered for the diagonalizable, one problem is not diagonalizable. So that I did in the class, but third one you can work out at home. So today I am ending the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.